So good afternoon, everyone. It's a pleasure to announce the last session of this 3-day conference. It's actually the title is something about novel devices, so we have put a mixture of different topics, including something about battery research, which actually Moritz Futscher is an expert on, and then also something about machine learning. So it's going to be some novel topics that might also reappear in a future edition of this conference. So it's a pleasure to announce Moritz Futscher, who was very busy because he already gave a nice lecture yesterday afternoon in the perovskite, in the mixed ionic electronic transport session yesterday, and his basically is now the second part with the title Quantification of Mixed Ionic Electronic Conductivity Using Current Transient Measurements. So he has been known in the field of perovskite, so PV research, and recently joined the EMPA research lab in Dübendorf, just half an hour from here. And we look forward to your talk.
Thank you for the introduction. Before I start, I would also like to thank Beat, Evelyn, for inviting the invitation and that I can present my work here, and even twice. I tried to make it the talks different from each other, but there will be some overlaps, especially in the introduction, so I apologize for that if you have already been listening yesterday. But they're quite different in the end. So what are mixed conductors? What I'm mainly interested in are mixed conductors. And in a material, you typically have arrangement of atoms or ions, and then you can classify them in terms of their band gap into semiconductors, insulator, or conductors. And in a real crystal, you always have defects, such as vacancies, substitutions, or interstitials. And if you have defects, that also means that these defects can be mobile, making them a mixed conductor. And the perovskites are one of the classes of mixed conductors, where we have both ionic and electronic conductivity, which is even affected by light. And then I've been doing my PhD mainly on perovskites, and now I'm working a bit both on perovskites and on solid-state batteries. And in batteries, we have also all kind of mixed conductors, where we have cathodes and we have anodes, where typically or ideally the conductivities of electrons and ions should be similar, and then they are separated or electronically isolated by a solid electrolyte, where ideally you only have ionic conductivity and electronically they should be isolating. And today I will give some examples of solid electrolytes. I show how we can use current transients to quantify ion migration in these solid electrolytes, and then apply the same methods to perovskites and see where are the differences there. But first, what is the conductivity? The conductivity is a function of both density and mobility. And quite often we only look at the conductivity, but here I want to show that it's important to actually know both of these parameters and how they change, because both of them are temperature dependent. So yes, first we'll show the current transient measurements. I will compare them to the frequency domain, to the impedance spectroscopy, showing that these results are comparable to each other. Then I will give examples for solid-state electrolytes and halide perovskites, and briefly we'll mention about emerging opportunities for halide perovskites in batteries. So these solid electrolytes, how do we fabricate them? We usually use a thin film approach because our lab is coming from a thin film solar cell devices, so we know everything about thin film processing. So we make them thin films, which is rather different compared to the typical battery community where they do very thick films and they make composites of everything. But this allows us to really study these materials in its pure phase. And we fabricate them by sputtering. So we have different material targets. In this case, everything that I will show is lithium lanthanum zirconium oxide, which is a very interesting material at the moment in the battery community as a separator. These films look something like this. They're very thin, smooth ceramic films. And then to quantify the dynamics, the ionic and electronic dynamics, we often crystallize them on, for example, MgO, and then have some metal fingers on top, which we can probe and put them on the Linkham stage, and then measuring actually with the pias everything. So how do we quantify these ions in these solid electrolytes? The idea is, here we always use symmetric contacts, either gold or copper, ideally better. And then in a steady state, these ions will be somewhat homogeneously distributed within our solid electrolyte. Then we apply a voltage bias, a large voltage bias, that all these ions will drift towards the interfaces until they accumulate it. And if we look at the measurement, this looks somehow like this, where we see a current transient and it starts to saturate. At this saturation, where this current saturates, is generally used to determine the electronic conductivities of these materials. Just with this simple relation, we know the voltage which we apply, and we measure the current. But to do this, we really need to wait until we reach steady state, and in these materials, that's typically hours. And then if we know that this is the electronic conductivity, we can subtract this part here, and then integrate over this curve, and then we can get an information about all the charge carriers which have moved in this device. And in this case, this is only ions, so this is the ion density. And here, just to show you, this is a function of bias, applied bias. As we increase the bias, this concentration increases until it starts to saturate, meaning that we have extracted all these ions which are mobile in the material. And here we made a test. So with sputtering, we have now the advantage we can sputter different materials next to each other, and we increase the weight ratio of one towards the other. So we can effectively add more lithium ion in our solid electrolyte films. And this is what we did here, is we added more lithium ions, and with this measurement we indeed see that the concentration increases while adding more lithium ions. So this directly shows that this method of estimating the concentration also gives follows what we actually do in the devices. The next thing is we're interested is in the time scale. How can we use the time scale to quantify this migration? And over the last 2 years, I measured many different solid electrolytes, also perovskites, and tried to come up with a very simple explanation. I tried analytical first. I didn't find any analytical which works both for crystalline and amorphous. So at the moment, I'm using a rather simple formalism where I assume if the ions are all homogeneously distributed and then I apply a bias, they will all start more or less moving at the same time towards the interfaces. And as they do, you will measure current until the ions have reached the interfaces. Then the current will decrease. So we can expect kind of a straight line and then a sharp kink. In reality, it's not as clear as this, but we still observe a clear kink, which is different for the different devices. And I now assume this is the time constant of where all the ions from the both interfaces have reached one of the interfaces. And then I can use this to extract the mobility via this formula, which is the drift formula. And there we see that these materials behave rather differently as it is expected for these materials. LZO is in the tetragonal phase, and as we dope them with elements like aluminium and gallium, they become in the cubic phase, which increases the conductivity of these materials. And gallium is slightly more repulsive towards lithium, so it's easier for lithium to migrate. And then with the method before, we can also now look at how the concentration of mobile ions changes with temperature. And this is now interesting because we now get the activation energy for migration, but also the activation energy for formation of these defects. And if we now take these two together, we can again come back to the conductivity, but now individually measuring concentration and mobility. And we see similar trends, just that now the activation energies differ from the activation energy for just mobility, because you also have thermally activated changes of concentration of mobile ions. And we use this, for example, as an example, we used it recently studying one of these solid electrolytes. And in solid electrolytes, we want to increase the ionic conductivity, opposite to what we do with perovskites typically. And one way to increase, as already indicated before, we could add more lithium ions. And here we indeed see we increase the concentration, we also increase the mobility as there are more lithium ions within the lattice, which then results in an increase in conductivity. Only if we add too much lithium, then the mobility starts to decrease again due to the formation of clumps within our device, which then hinders the mobility. And then with the transients, we can also get information about the electronic conductivity. And here we see that we could increase the ionic conductivity by many orders of magnitude while keeping the electronic one very low, which is desirable as a separator for solid-state batteries. Then to show you that this method is actually applicable, we have to compare it to other method. In this case, I show you impedance spectroscopy. Whereas in impedance spectroscopy, We measure the impedance by applying an electric field and measuring the current, as shown in this formula here. And then this is typically represented in these Nyquist plots, where the conductivity is now directly related to the resistance, which is the diameter of this diamond plot, this Nyquist plot as shown here. So there's the formula of the conductivity. If we know the resistance, we can directly know the conductivity. Another way where we can look at the conductivity is if we look at the time constants, but from the RC time constant, there the data would look something like this, and also from this time constant we get the conductivity. And here, I don't go into detail too much here, but I showed it yesterday that there's a different representation, which is the modulus, and it has some advantages. For example, as we have polarization at lower frequencies, these are completely not visible in this modulus representation anymore. So for some of the devices, it's not easily readable with the impedance, but with the modulus, you can more easily get the conductivity values. And these are now the impedance spectra for these 3 solid-state electrolytes. They now compose of 2 semicircles. One is bulk and one is interface migration, and a polarization effect. And this is the circuit which we use to fit this. And if we use then the effective conductivity, which is the sum of the grain boundary and the bulk conductivity, and compare this to the transient measurements, we see that both in the time and the frequency domain, qualitatively they very much agree. Quantitatively, there's still a slight offset. The transients are slightly slower in time scale than the impedance. And we currently suppose that this is due to the case because now all the ions have actually to move through the whole bulk, whereas in impedance, you oscillate the ions around and they don't necessarily have to go through the same migration path as going to the whole device. And we're doing at the moment also simulations of how this migration path works in those. And this seems to follow more or less what we show in the time domain as well. Okay, so this is all for solid electrolytes so far. So how is this applicable to perovskites? And here I use 2 examples for perovskites. So one is a 2D perovskite, and one is a 3D perovskite, cesium formaldinium lead iodide. And I will start with the 2D perovskite. So this is a nice perovskite because it has a very low ionic conductivity. And you see that here in the impedance spectrum, this is very flat. As we increase the temperature, of course, we still see this increase in capacitance at low frequency due to polarization. And this is the Nyquist plots to get the ionic conductivity. And we get a nice Arrhenius law for these devices to get the ionic conductivity out of this. So how does this now look in the time domain? And here, what we do is we now apply a voltage bias of 0.4 volts and measure the current response while applying and then also while going back to 0 volts. And if we zoom in to this part here, we get these characteristics. And there you see already this kink, which we see here, moves down in time scale, which is, if we look at the solid electrolytes before, this was very characteristic for ion migration. And if we now use this, we can follow this and look at the time scale for ion migration in these devices. So these behave very similar to solid electrolytes. And again, we can look at these offsets here at the current to estimate the electronic conductivity of these devices. And this is what we get for these devices. We have the mobility, the concentration, and the conductivity calculated by the combination of these 2. And we see that the activation energies are different if we look at just conductivity or mobility. Again, showing that it is important to look at both how the mobility change and how the concentration change. And here we see that the concentration increases until, again, it saturates at some point, probably because there are not more ions in the device which can migrate. And how does this compare to impedance? In this case, this compares very well to impedance data, which we've seen, which is nice for this. But this is a special case because in here we have low ionic conductivity, but even lower electronic conductivity. So here the difference between ionic and electronic conductivity is rather large. That's why they behave very similar to solid electrolytes, which are also only ionic conductors. It gets a bit more complicated once ionic and electronic conductivities are similar. So for this, we look at this device here, cesium formaldinium lead iodide, with different concentration of cesium added in there. And here these are the modulus plots where we get the characteristic time scale for ion migration. And as we add more cesium, this time scale shifts to lower times, which means that the ion migration gets slower, which is because of the lattice contraction to adding cesium into these devices. And this you can see here. There's a nice trend by adding cesium in there, the ion concentration goes down. Now, if we shine light, we see that now this time scale shifts to higher frequencies, which would be indicative to a faster ion migration. As we also have seen and heard during the conference, there's these ion migration in perovskites is light activated, and we see that the conductivity in light increases by 2 orders of magnitude, roughly, for these devices. We can, with the transients, we can now also look at the electronic conductivity. And here we see now the dark and the light. There's also an increase in conductivity, but this increase seems to be much smaller compared to the increase in ionic conductivity. So if we now would compare the case in the dark, the conductivities are much closer together than in the case of the light. And this is how this looks then in the transients. So a perovskite in the dark, if we apply a voltage bias, we typically get a behavior like this. So we have a certain current which increases and then saturates again. So this is explained as you change the energies at the interfaces. So basically that the ions move towards the interfaces, which changing the extraction current which you have. So it's basically a coupling between electronic and ionic effects. So this can definitely not be used to estimate the concentration of mobile ions, because this is all electronically dominated. As we increase though the light intensity, we increase the ratio between ionic and electronic. And at some point at one sun here, this more looks like the curve which you would expect for a solid electrolyte, where we have more ionic conductivity compared to electronic conductivity. And if we now, here's the solid electrolyte, how this looks, where we know that the ionic conductivity is much higher than electronic. Here we have them more or less equal, a bit higher ionic still. And then here we have the ionic clearly higher, where we see this characteristic shape, which is also for pure ionic conductors. If we compare the values which we get from impedance and transient measurements, we also see in the dark they differ quite a bit from each other, because there's probably because there's a crosstalk between ions and electrons, and then this transient measurements probably are not as feasible anymore, and we need much more. We need definitely simulations to understand this better. But it seems that in the light, where the ionic conductivity is higher, and these measurements again coincide rather well. So it seems that these measurements are feasible as long as the ionic conductivity is much higher than the electronic conductivity. As soon as they are similar, they start to interfere. Now I want to switch a bit and look into emerging opportunities for these perovskites in batteries. We already heard a talk yesterday from Johan about memoristos, how we can use them in memoristos, and I want to quickly mention how we can use them in batteries as well. So in a battery we have an anode and a cathode, and between the anode and the cathode we basically shuffle around this lithium ions to charge and discharge, and they are isolated by this electrolyte here. And perovskites have actually been used successfully already for anode, electrolyte, and cathode. And I'm going to just show you 3 examples where this has been done. Here, for example, they used it now as an anode, 3 different perovskite conformation in lower dimensions. And for the 1D, they got a capacity, so how much charge you can get out of your anode, reversible, of almost 600 milliamp hour per gram, which is a very high value. If you compare to graphite, which is at the moment the most used anode, it's 370. So this is indicating it works as an anode. It's probably a conversion mechanism where the lithium actually reacts with the lead. It completely decomposes the perovskite, but this seems to be somehow reversible. So this is already quite interesting from concept itself. Then here, Karano Sada showed that you can also use it as a cathode. So what they did here is they fabricated 2D perovskites, which is more like a conventional cathode is working. You have 2D layers and your lithium ions go in and out. And here they managed to do a 2D perovskite layer with actually the lithium ions go in and out, and they could use it as a cathode. And then I think for me most interesting is that you can also, since they're light active, you can now use something like a photo cathode. Where here, in Michael DeVolder's group, they showed that they have a perovskite battery, use it as a cathode. You can discharge it, and then just by shining light on it, they can charge it again, because it's photoactive. And this is a very interesting concept, which we are also actively at the moment trying to find materials which can do that. Of course, everything gets very complicated, and it's very difficult to understand these processes, but fundamentally it's quite interesting. And how do we do this? We typically fabricate a thin film battery, like this, all with PVD processes. We have our transparent back contact with a blocking layer. Then we put our cathode here, which is a mixed conductor, which is then with a solid electrolyte, which separates the anode from the cathode, which is a pure ion conductor. And then we have our lithium metal anode, which is evaporated. And the nice thing about this, if we have a light-active mixed conductor, what could we expect out of this? We could potentially achieve Coulombic efficiencies above 100%. What does that mean? Coulombic efficiency is the ratio of the energy you put in towards the energy you get out of your battery. And of course, if you have a photoactive material, you generate energy in the process. So you have a Coulombic efficiency above 100%. Then, in principle, you can improve the fast charging capability. So in batteries, there's a lot of focus of increasing the conductivities of your mixed conductors, because how fast you can charge and discharge your battery is strongly governed by the conductivities of these materials. And so as we go thicker in these materials, we need to add a lot of conductive additives like graphite to get the conductivity up, which again decreases the active to passive ratio. So because you have less active material, less cathode material, because you add a lot of additives. If we could do this by light, that could also be potentially interesting, if we can just increase the conductivities and thereby allow fast charging of batteries. And then, as one example I showed you in the last slide, there are some work where people charge the battery with light, which is also very interesting, but I feel that there are still many things which we don't understand yet, and most of the theories, how we explain it, maybe are not fully correct yet. And what are possible candidates which can do that? Halide perovskites, I've shown you, and all kind of materials which can be in principle mixed conductors. I've just noted a few: selenium, because this is the one which we tried so far, which works, tellurium, but then there could also be many different combinations like CIGS, castorites. All the typical solar cell materials can in principle are also mixed conductors. And for example, CIGS is a very good ionic conductor, and it's a very good solar cell, so you can use it now properly as a photoactive cathode. And we are actively trying to do this at the moment, but we are not there to show anything yet, unfortunately. What I can show is with selenium. And here, first of all, we fabricated this battery, and here you see the typical characterization of such a battery. On the left, you see the capacity of your battery, and then on the right, you see the Coulombic efficiency. So how efficient is your device? How much current get you out for the current you put in? And then this is typically plotted as C rates. And a C rate means, a C rate of 1 means you charge and discharge your battery in 1 hour. And a C rate of 0.5 means 2 hours. So it's related to how fast you charge and discharge your battery. And the typical characteristic is if you have low C rates, so low charging and discharging, you have higher capacities. But as you increase the C rate, you have resistive losses, so you decrease your capacity. Still, these values are pretty good, because commercially, cathodes at the moment are intercalation cathodes. They typically have values of 150 milliamp hour per gram. Go up to 200 for the best ones. But this is a conversion material, so it's rather different than an intercalation, so the whole material changes. And these materials reach very high capacities. And these especially can be used very well in a thin film system, because you have a lot of volume expansion. In this case, this expands by about 40%, which in a bulk system, this is not easily possible anymore. And here you see the impedance of such a device with increasing light illumination. So this impedance is governed by the selenium layer, which is the most insulating layer in this device. And as we increase the light, we see a strong increase in conductivity, which is already nice. And one thing here which you can see is this is ambient, and even ambient light, which is just inside the glove box, already has a huge effect on selenium, which is also the reason why selenium was one of the first materials which was used as a solar cell. because it's very, very photoactive. And then here some of the cycling data. So this is the capacity over different cycles. So we cycle it, each point is basically 20 hours now because it's 0.1 C. It cycles for many times, and then there was just a black cover on top of the cell, and then by just removing the cover, just with the ambient light, we have a very strong effects on these batteries. And we see that in this case we increased the capacity by almost 40%, which is a lot, and probably due to the increased conductivities, which reduce resistive losses. And then if we look at the Coulombic efficiency, we also see Coulombic efficiencies above 100% in these devices. So with this, I'm in a conclusion. I could talk a lot more about batteries, but I tried to keep it limited here. I showed you that when looking at ion dynamics, it's important to look at both how the mobility and how the concentration changes to actually get a bit more fundamental insights on how these processes are dominated. Current transients can be used to determine both concentration and mobility. And I showed you that this works for a wide range of materials, although we have to be very careful in perovskites, as we know that the electrons and the ions interact strongly with each other, and as soon as the conductivities are similar to each other, so such simple methods as shown here don't work as easily anymore, and we definitely have to also use simulation to understand this better. Yes, and then these perovskites still have many new emerging applications which are interesting to study, like memoristos or batteries, for example. Then I would finally thank my group, where I'm currently at EMPA, especially the people listed here, which helped in device fabrication and the characterization, and the collaborators, Mustafa and Christian, for fabricating the perovskite devices, and Harry and Henry for the 2D perovskite, as well as Juvana, and then funding. And you all for your attention.